All right, we're starting today. We're going to go through the different shapes, and we're kind of picking up where we left off on Friday. Friday, we ended by talking about steric number. Steric number is how many electron groups are around a given atom when we're evaluating it for the purpose of shape. And so we look at the center atom and we evaluate, okay, how many things is it bonded to and how many unbonded pairs of electrons are around it as well. And so in total, there end up being a total of 5 different steric numbers. Now, I don't have enough model kits for everybody. I try to put one between every 2 or so of you, for those of you that were kind of close together. There are 5 shapes that we're working off of. And so on each side of the room, I've given you kind of a key here to look at. If you want to build the shape yourself, just so you can kind of see it, feel it, get an idea of what it looks like 3-dimensionally, this is the way to go about doing it. So starting off with steric number 2, that's the gray silver ball with a steric number of 2, where I've got 2 groups, most likely bonding groups. What I have here is a linear shape. The linear shape here, like what we see in carbon dioxide, is going to yield for us an arrangement, a bond angle, or if I'm looking from here to there, I'm looking in the neighborhood of 180 degrees, which makes sense. It's a line. Lines are 180 degrees apart from one end to the other. So this is the simplest of the shapes. You do see it in certain kinds of situations. Carbon dioxide is a good example of those. But it definitely gets more complicated from here. Let's move on to steric number 3. In steric number 3, we're looking at the tan or beige center atom here, 3 groups around it. Now we can start to see some variation, some variability. Not only do I see this triangular shape, which in geometric terms, we're not going to call it triangular. We're going to call it kind of its close cousin, trigonal. And so trigonal geometry, in this case, trigonal planar, because not only is it triangular in shape, it's also 2-dimensional. This can come in a couple of different forms. What's common to both forms is that the bond angle here starts at 120 degrees. After all, again, if we think about this as a triangle, if a circle is 360 degrees, 1/3 of that circle would be 120 degrees. Now, what's important to know is that there are differences once we start looking at whether we have bonding sets or non-bonding sets. So when all 3 of the dimensions, all 3 of the sets here are bonds, the name of this shape is trigonal planar. If one of those gets exchanged for a lone pair, however, remember, the lone pair doesn't actually show up. We're only looking for molecular shape at the atoms. The atom shape, the molecular shape of this molecule, just looking at the atom, would be bent. Bent can also be called V-shaped or angular. What's important here and this goes for pretty much anything. If we start replacing bonding sets with non-bonding sets, the bonding sets are shared more evenly. They're distributed. That electron density is not just in the bottom around the center atom, it's also around the other atom in the bond as well. And that diffuse nature of the bond makes the repulsion a little bit less. But if I have a non-bonding pair, and for those non-bonding pairs, these tan spheres with the little pegs on them can be used. If I have a non-bonding pair like this, what I can see is that this set of electrons isn't shared. It's sitting directly on the center atom. So from a repulsion standpoint, this is a lot more repulsive than the bond was. What does that mean for my bond angle? Well, it means that this bond angle here is going to get shrunk down. How much does it shrink down? Well, in the case of chlorocarbene, it gets shrunk down to 109.4 degrees. For us, we're not going to get that fine about it. We're just going to say that it is definitely less than 120. And that's as detailed as we need to get. It's going to be less than 120 degrees in that circumstance. So that's steric number 3. And so steric number 3, the domain geometry is trigonal planar. Every time we talk about domain geometry, we talk about kind of the first case, the all bonds case. And then molecular shape can be derived from that based upon how many lone pairs there are. With steric number 4, the primary shape here with steric number 4 is called tetrahedral. And there are 3 subshapes. So if you're looking for tetrahedral in your kit, it is the black center atom, 4 different ranges. This is our first example of a truly 3-dimensional shape. Linear, 2-dimensional. Trigonal planar, 2-dimensional. Tetrahedral, 3-dimensional. And that 3rd dimension comes out because if we had something that was 2-dimensional, where I got my center atom in here, and I've got like a square-shaped kind of molecule like that, we would expect all of these bond angles to be 90 degrees. However, with a tetrahedral shape, the bond angle that we actually get is 109.5 degrees. So by going from 2D to 3D, we're gaining an additional nearly 20 degrees of separation between the groups. And that's why we have to think about things 3-dimensionally instead of 2-dimensionally when it comes to molecules. Now, from this perspective, again, there are 3 different subshapes here. The first being the tetrahedral itself. If I take off one of these and put on a lone pair instead, what I get left is something called the trigonal pyramidal shape. Now, where does that come from? Well, again, if I look at this molecule here in 3 dimensions, I don't have a topper on it anymore. But I do, if I think of the center atom as being the top of a pyramid, I do have a pyramid. Because this center atom is raised from the other 3 atoms. Why is it called trigonal? Well, because of the base. The base of this pyramid is triangular, as opposed to square or octagonal or any other kind of geometric shape that you could think of. In terms of bond angles, we know that this lone pair is going to squeeze these bonds together a little bit. How much do they squeeze them? Don't know. Or at least we don't have a definitive rule of thumb. So we're going to use less than 109.5 degrees as our mark here. Now in ammonia, it's actually 107 degrees, but that's not a hard and fast rule. If I looked at hydronium, H3O+, I wouldn't necessarily get 107 degrees for that particular molecule. So we can't use, well, if you put in one lone pair, it's this, and if you put in two lone pairs, it's that. We can't use that. That's not definitively accurate. It depends, molecule to molecule. So that's why we're going to speak more generically. If I have two lone pairs instead of just one, I'm back to this bent or V-shaped kind of configuration. Only difference between this V shape, this bent or angular shape, and the one that we saw with steric number 3 is the bond angle itself. Remember, the bond angle in the previous steric number was less than 120. This one's less than 109.5. Now, there's one other thing that we want to introduce here. Now that we have three-dimensionality, we need to talk about how to represent that three-dimensionality when we draw on two-dimensional paper. And the way that we do that, you can see it in these drawings here, is through the use of what are called dashes and wedges. So these wedges, these represent atoms, bonds that are coming out of the paper at whatever angle is being shown. Now, if you want to kind of show this to yourself, grab your model kit and hold it straight in front of you, holding two of the pegs. These two pegs, along with the center, would represent a two-dimensional plane kind of right in front of you, like you were looking at it on a piece of paper. The one that's pointing directly to you, that's what would be represented by that wedge. And so you can see it is coming out from the direction that these ones that you're holding in your fingers are going. That's a wedge. Dashes represent atoms, bonds that are going into the paper. Again, at whatever angle is trying to be depicted. So again, looking at this from the way that you're holding it, that one that is going away from you, that would be represented by those dashes. Now, as we get to more complicated steric numbers, we're going to see dashes and wedges in all of them. What we're also going to see in the more advanced structures is we're going to see a difference of position. Right now, everything we've talked about, all of these positions have been equivalent so far. They've all been exactly the same distance apart, 120 degrees, 109.5 degrees, 180 degrees. When we get to those higher order structures, it's not going to be the same. But before we get to those, let's see what we've picked up from these first three sets of structures. So I've got ammonia here, NH3. Which domain geometry would we predict for the nitrogen in the ammonia here? So remember, domain geometry is based upon steric number. What is the steric number of the nitrogen here? What shape does that steric number predict? So I'll give you a minute, put in a preliminary answer. Right. Show me on your fingers. What is the steric number for the nitrogen? Yeah, it's 4. I've got the 3 bonding groups and the 1 non-bonding group, so 4 in total. With a steric number of 4, we would be looking at the tetrahedral domain geometry. Remember, all that domain geometry tells us is what shape are we starting from. We aren't evaluating any differences between bonding and non-bonding yet. What shape are we starting from? So with a steric number of 4, we're starting from the tetrahedral geometry. All right, let's take it one step further. Same structure. Now we want to know what is the molecular geometry. What is the actual shape that ammonia takes on? And so for that, we need to evaluate bonding versus non-bonding electrons. So if you have the model kit in front of you, you could recreate this. Take your tetrahedral and you pop off one of those bonds to represent the lone pair of electrons. The question is, what is left when you do that? What's left is you've got a pyramid with a triangle-shaped base, trigonal parameter. So letter D here. Now, one thing that I want you to keep you in mind, when we get to the end of this, I'm going to show you a summary table. That summary table is going to go with you wherever you go. So next week's quiz, the following week's exam, you're going to have that table at your disposal the whole time. So it becomes a matter of really just knowing the difference between bonding and non-bonding, rather than having to memorize all of the different shapes and configurations. All right, last question here. We've got our structure. What's the bond angle in this structure? Right, so you should have been possibly torn between 2 different answers, letter C and letter E. Letter C is the typical bond angle for tetrahedral, 109.5 degrees. What we have to remember is that this lone pair on top is going to impact the size. It's going to squish everything down. And so we're going to see less than 109.5 degrees. Now, how much less? It depends. We know from the previous slide, it's like 107. So that would be letter E. If we're talking just more generically, yeah, we know it's going to be somewhere between tetrahedral and a full-on squared up right angle. Chances of it going all the way to right angle, really slim. All right, any questions with kind of where we've gone so far? Okay, now it gets a little bit more complicated. In fact, I would argue that this particular shape, the trigonal bipyramidal shape, is the most complicated of the 5 shapes that we're looking at. Because this shape not only has 4 different subshapes, there's one actually that is missing that I'm going to have you draw in from this slide. We also get the introduction of what are called axial and equatorial positions. Now, let's talk about those briefly here. What do we mean by each? Well, what you should notice is if you hold your model tip to tip like this, you see that you pretty much have the marriage in this particular steric number of the linear shape and the trigonal planar shape in the same model field, in the same model. So we have linear, we have trigonal planar, they're both here at the same time. The linear portion we refer to as axial. Why is it axial? Because those 3 atoms form an axis through the middle of this molecule. I mean, think about it spinning on that axis like the Earth spins on its axis. So that's the axial position, the top and the bottom here. These 3 positions in the middle are known as equatorial positions. Why? Well, let's go back to this globe analogy. You know, Earth sits on its axis and spins. Well, halfway between north and south on the globe would be the equator. The equatorial positions are halfway between the top and the bottom positions in the axis. Now, this is referred to as the equatorial plane because it is a 2-dimensional plane in that equatorial position. And so because of that, we have 2 different sets of bond angles to be concerned with. The axial positions are 180 degrees apart. Makes sense. That's the linear portion. The equatorial positions are 120 degrees apart. Again, makes sense. That's the trigonal planar part. Where it is different is where we have to consider how are they related to each other. And they are related to each other at 90-degree angles. The other thing that we have to consider with this steric number is the concept of repulsion. In repulsion, we are concerning ourselves with what do those lone pairs do? Where do we find them? Well, because the equatorial positions are the furthest apart from each other, lone pairs go into that equatorial plane. And so the first position that we see is if we remove one of those equatorial spots, what we get was called a seesaw position. Now, the seesaw position is a little bit hard to see when you're holding it like this, but if you turn it 90 degrees, you can get the basis for why it is called seesaw. That's the seesaw position. One lone pair in the equatorial plane. What does that do to the bond angles? It squishes all of it. So we go to less than 180, less than 120, less than 90 degrees. All of them get pushed on by that lone pair there. With the introduction of a second lone pair, things actually simplify a little bit. You can see that we don't have any more equatorial bond angles because there's only one in the equatorial plane. So the bond angles here just simply shift to 90 degrees and 180 degrees. There is no 120 degree bond angle because there's no second bond in this equatorial plane. The third position, well, what if I have lone pairs in all three equatorial positions? Well, if that happens, which it does, what we're left with is a pretty familiar looking shape. All that's left is I've got the three remaining atoms in a line. This is linear. And a linear molecule only has one bond angle, 180 degrees. Like I said, this is the most complicated of the shapes. When we get to steric number 6, it actually does get a little bit easier. For one, there are only 2 subshapes other than octahedral. So we've got 3 subshapes instead of 4. The other thing is that the bond angles significantly simplify. So all of these angles, so our axial positions are still 180 degrees apart because now we have 4 objects in that equatorial plane. The equatorial objects are 90 degrees apart, and axial to equatorial is also 90 degrees. What's interesting about the octahedral, all of the positions in the octahedral are equivalent. So we're back to the same kind of stuff that we saw with tetrahedral, the same kind of stuff that we saw with the trigonal planar. Every single one of these positions is equal, and you can prove that to yourself. Just grab your octahedral shape, grab any other lobe on that shape. You're going to come up with the exact same structure, the exact same look every single time. All 6 positions are equal. So when we have bonds in all those positions, it's called octahedral. Since all 6 positions are equal, there is no difference between axial and equatorial. So any electron group can be pulled off. You'll get the same shape regardless. The shape here is called square pyramidal. All that we know about square pyramidal, the bond angles shrink. The bond angles shrink. No longer having axial to axial, no longer having, we're just looking at 90 degrees being shrunk all around. Now, other interesting thing, that second position is always going to be the opposite of the first one. Minimize repulsion, get them as far apart as possible from each other. What's left is the square planar. Because those two positions are opposite each other, the pushings basically cancel each other out. We're back to fully just 90 degrees. So we didn't get a chance to. Here's kind of our summary chart. So again, this is the kind of thing that's going to travel with you. It's not going to look exactly like this. It's actually going to be a little bit more layered. We're going to have some extra information in it from stuff that we're going to talk about Wednesday and Friday. But this kind of thing is going to be the kind of thing that you should be expected to know how to use. Here's what I'm going to tell you. There are some practice documents. So as you're going through this assignment, if you're finding yourself getting stuck, I'm in the process of publishing a video that walks through these practice problems as well as these practice problems, and putting it up on YouTube, posting it to Blackboard. If you're getting stuck on here, feel free to watch through those and use them to kind of figure out how to evaluate. It always comes down to you have to draw it correctly and you have to evaluate it correctly based on steric number and those other considerations.